Good afternoon, everybody. So today I am going to give the top. My topic is on the overview of various IRC codes and detailed study of standard loadings and load combination as per IRC 6. So I will start with the contents. My content will be overview of IRC code for the bridge design and load combination as per IRC 6. It's a brief content. So when we are designing the bridges, what are the various codes we are following? First and foremost code is IRC 5, 2016 section 1, which gives the general features of the design. General feature means it gives the classification of types of bridges, it gives the hydraulics, and it gives the site selection that will be seen in the subsequent slides. Then there is a code which is majorly covers the loads and load combination, that is IRC 6, 2016 or 2017 is a revision of it. And third code which is used is a substructure design and foundation, this is IRC 78. These are the basic codes which use the loading analysis part. And then IRC 112 2019 code is there, which gives the design. It is equivalent to IS 456, which gives the design of elements, structural elements. And one more code which is recently given introduced is IRC SP 114, which specifically gives the guidelines for the design of the seismic conditions, which will be covered by in the next section. Mr. CVR Murthy will be covering the seismic design and seismic loads. Now, when we go for the IRC 5 2015 section 1 general feature of design, this course covers the definition of bridges, definition, classification, component of bridge structure, and collection of data. Yesterday, Mr. Vinay Gupta has given the brief introduction of the classification of the bridges, different types of forms of bridges, which are all covered in IRC 5 2015. If you go for the introduction bridge, the definition of bridge is, the bridge is a structure having a length of 6 meters and above between the inner face of the dirt wall for carrying the traffic and other moving load over a depression or obstacles such as channel, road or railway without closing the way beneath. This is the basic definition which has been covered in IRC 5. And again it is further classified as a major bridge and minor bridge. The minor bridge is a bridge which is having a length equal up to 60 meters. From 6 to 60 meters it is a minor bridge, and for above 60 meters it is covered in the major bridge. So again, further classification of the bridges is based on the function of the bridges. It can be a river bridge, it can be a viaduct, it can be a grade separator. Again, it is a road over bridge, road under bridge, footway bridges, underpasses, flyover, and subbridge. And second, the classification is based on the length again. It is a culvert bridge or culverts or bridges. Based on length. Culvert, the length of the bridge less than 6 meters is a culvert. Above 6 to 60 is a minor bridge, and above 60 it is a major bridge. So when your further classification based on the superstructure is given, so it's a form of superstructure which is adopted. It can be an arch bridge, solid slab bridge, voided slab bridge, T and T-beam bridge, T-beam and slab bridge, suspension bridge, cable stay bridge, extra doors, box girder, single multiple box cells, which is covered in the classification under this type of superstructure. And again, the bridge is further classified based on the support systems. it is simply supported, whether it is simply supported, whether the bridge is continuous, whether it is integral bridge, balance cantilever, and cable supported bridge. So again, based on the support system, it has been classified. So that part is, the detailed part is given in IRC 5, which was yesterday covered by Vinay Gupta also, sir. So when you see the components of the bridge, so component of bridge is, one part is, top part is superstructure, and bottom part, it is a substructure. So in substructure, again, there is a foundation, there is abutment. I will highlight the. So this is a substructure part, this is a superstructure part, and substructure again it is covered as abutment, piers, piles, pile cap, pier cap, bearings, then parapet wall, deck slab. These are all the parts of the components of the bridges. Now substructure covers basically piers and abutment, pier cap, abutment cap, bearing, pedestal is covered in the substructure, which is given in IRC 78. Basically, how to design that. And all other miscellaneous components are railing, parapet, curbs and footpath, bearing cord, drainage spout, expansion joint. All are the miscellaneous components of the bridges. So when you are designing the bridge, you have to collect the data from the site. All the detailed information for complete and proper appreciation of bridge project shall be included in the project document, and those are general data including maps, topo sheets, plans and topographical features has to be collected. Then you have to collect the hydraulic data, which was yesterday covered by by Mr. Sanjay Khere and Mr. Desai. The geological and seismological data is also very important, because geological data is required to find out the founding level and founding strata. Because our bridge should be founded in the sound founding strata, so there should not be a settlement or there should not be any failure during the seismics. And then subsurface data. Subsurface data includes the soil data, which is required while designing the bridges, and loading other data, whether it is to be designed near the industrial structure, whether we have to take the loading of special vehicle, that data is also very important. And traffic data is required. Then construction material availability nearby the sites has to be data has to be collected. Any special design requirement, aesthetic, as per the authority, that we have to find out. And then existing any services. When you are designing the flyover, there are a lot of existing services of corporation and other lines has to be identified before planning the bridge GAD. Then availability of labor, accommodation and other authorities. Now we have completed the review of the IRC 5. Now overview of the IRC 78/2014 section 7, which gives the foundation and substructure. This code covers the following topics and guidelines of the design of subsurface exploration, means soil geotechnical exploration. It gives the basic design codal provisions of open foundation, well foundation, pile foundation design, and substructure design, that is pier cap, and abutment cap. So in the IRC 112/2017, that code of practice for design of road bridges is newly introduced, which is equivalent to IS 456 type, and giving lot of detailed overview of the design of analysis and design of the bridge based on the ultimate limit state and serviceability conditions. So this code covers the basics of design, material properties and their design values. It covers the analysis part. It covers the ultimate limit state design for axial and bending moment. And the serviceability limit state covers the stress check within the permissible limit, crack width and deflections. So here if you see the basic of design is covered in two parts. One is limit state method and another is working stress method. So IRC 112, which has been introduced recently in 2016, it covers, we have to design the bridges now with limit state method only. So it covers the ultimate limit state and serviceability limit state. In again ultimate limit state, it covers the limit state of equilibrium and limit state of strength. This topic will be in next session will be covered by Mr. Umesh Rajashirke in detail. And again, this is serviceability limit state, covers the limit state of internal stresses, crack control, deformation, the limit state of vibration and limit state of fatigue. So further, one more code which has been recently published, special publication. It is one more guideline for the design of road bridges considering the seismic design. This code covers the conceptual design, seismic analysis method, design, seismic design methods, design of bridge component, ductile detailing of structure, and seismic isolation devices. This topic will be covered in a subsequent section by Mr. CVR Murthy, which will give in detail the seismic design and detailing of highway bridges on 11th of December 2021. Now, these are the basic codes which I have given, overview I have given, which are used for the design of bridges. So what exactly is the process of design of road bridges? What is required? It requires the planning. In planning, again, site collection data, hydraulic calculation, preparation of general arrangement drawing, estimate and technical sanction, tendering process, award of contract to successful bidder. So this is basically initially it is required for any construction of bridge because planning is very important. Then when planning and successful bidder is awarded the work, then comes the detailed design of bridge. So in that we go to do the load calculation based on the general arrangement drawing. Then part comes the analysis of structure to find out the bending moment, shear, torsion. Then the design of the section as per the analysis and preparation of the working drawing for execution purpose. So when you are designing it, you are not the final authority. There should be the person who will approve your design. That is design circle of PWD or proof checking is done from the external agency or from the approved IIT professors. So that is very important. So approval from authority is very important. Checking of the design calculation and issuing good for construction drawing for the execution purpose to the contractor. So that is very important. This is the process of design. So now we'll come to the topic for the load and load combination as per IRC 6/2017. So when you are the first and foremost is the process of design is you should know the general arrangement drawing. When you are calculating the load, if you don't have the general arrangement drawing, you cannot calculate the loads. So you should know the span arrangement, tentative sizes of the components of the bridge components, type of superstructure. Then only you can start the designing. So initial primarily the general arrangement drawing is very important. Before designing of any bridge, you should know the architectural drawing. When you are designing any house or first you go to the architect, get the plan done, then you will go to the structural engineer for the design. So that is very important. So in that, what are the loads which are applicable for the design of bridge? One part is first and foremost load is dead load. Second is lie load. Then longitudinal forces, horizontal forces due to water current. Then buoyancy, wind load, seismic forces, centrifugal forces, earth pressure forces for the design of overburden retaining wall, and temperature effect for the integral structures. So these are the basic loads. So one by one we'll go in detail. So what I told you, whenever we are designing any bridge, we should prepare the general, we should get a general element drawing. So this is the type of general element drawing which I had taken from one of our projects. And so this general element drawing gives the span arrangement, what is the founding level, what is the soffit level, what is the HFL, what is low water level, bed level covering. So this all details are given in the general element drawing before you are starting any of the design calculation. This is a very foremost drawing which is required during planning stage. And this is required for estimation purpose also. If you see, this is a superstructure part. This is pier cap, pedestal, and bearing above it. This is the pier, and this is foundation. So this dimension and cross section we should know foremost, which is giving the founding level and all this thing as per the geotechnical report, soil exploration report. So first and foremost load which comes in the mind is the dead load. Major dead load component we have to calculate based on the density of the material. So this is the dead load is nothing but a sulfate of the bridge elements. That in sulfate it can be a dead load of the deck slab, then girder dead load, wearing cord or superimposed surfacing load, parapet and railing SIDL. This is the first dead design load to be calculated for the design of bridge. So how we are calculating? It is cross-sectional area into density of the material. That is very important. So when you are working out the dead load, you should know the density of material which is already given in tabular form in IRC 6. If you see, so here volume of a small calculation is shown. It is that everybody can do. That is the cross-section area into density gives the dead load. But whether it is total load or UDL, that you have to ensure before analyzing the part. So when you are saying load calculation, without load calculation, you cannot do the analysis. So primary in any bridge design or any structural design, load calculation is very important. And that too, dead load calculation. So for dead load, you require the density of the material and cross-section of the element. In IRC 6, one table is given. One table is given which gives the notation of the type of load and forces. So when you are saying it is dead load, then IRCC gives the notation G. When it is live load, it gives a notation Q. Snow load, GS. G means dead load of snow. S means snow. Impact factor on vehicular load, QIM. Impact factor due to floating body. Vehicle collision load, wind load, W, water current load, longitudinal forces caused by the tractive efforts of the wheel or braking, centrifugal force, buoyancy and air pressure, including live load surcharge. This table is given in the IRC. And temperature effect is FTE, deformation effect is FD, secondary effect, it is usually considered in the pre-stressing or in structural steel design or composite superstructure. Erection effect, there is a construction methodology, what is adopted, what are machinery used on the superstructure, that if erection effect you have to consider while designing. Again, wave pressure and grade effect. In IRC 6, again, the table is given for the unit weight of the material. The table you have to follow while calculating the dead load. So they are given the density based on the type of stones, again concrete type, asphalt concrete, cement, plain cement concrete density, and pre-stressed concrete density. Everything is given in the tabular form. In the next slide, so this is the what we have covered is the dead load calculation based on the IRC 6 and density is given. Now main load in any bridge design is the lie load. So what are the classification of lie load? Lie load is classified into vehicular lie load and pedestrian lie load. In vehicular lie load, again there is a class 70R load is there, class A loading is there, class A is there, and class B load is there. There are 4 types of loads. Usually in the design of bridges, we take class A loading and 70R load, which is again further classified as wheel load or track load. One more load which is used for the industrial corridor is newly introduced is special vehicle load. That is known as SV loading. So, if you say 70R track vehicle, 70R track vehicle is having a total load of 70 ton with a center to center distance between the two track is 2.06 and ground contact is 4.57 meters. For track vehicle, nose to tail is successive track vehicle which are following is 90 meter is the distance between the two successive vehicles. It should not be less than 90 meters. So this is very important while you are analyzing the lie load analysis for finding out the bending moment of the superstructure and reaction on the substructure. And second is the next slide is 70R wheel vehicle, which is equal to the 100 ton total load with a total length from tail to nose of the axle is 13.4 meters. And maximum load for the wheeled vehicle shall be 20 ton for single axle and 40 ton for a bogie of two axles spaced not more than 1.22 meter centers. 70R loading is applicable only for bridges having carriageway width of 5.3 and above. Why it is taken 5.3? Because the edge distance of the vehicle axle wheel and the curb is minimum 1.2. On both the side it is 1.2. So it is 2.4 plus 2.9 meter is the width of the vehicle. From 2.9 is the width of the vehicle. So it becomes 5.3 meters. So class 70R wheel or 70R track is only taken when the bridge is having carriageway width of more than 5.3 meter. For multi-lane bridge and culverts, each class 70R loading shall be considered to occupy 2 lanes and no other vehicle shall be allowed in these 2 lanes. When it is a 2-lane bridge, so only one class 70R wheeled vehicle or 70R track vehicle is no other vehicle is passing. That is also given in detail in IRC 6 in tabular form. So these are the total wheeled vehicle. The total load is 100 ton. So there are 4 17 ton axle load, 2 12 ton axle load, and 1 is 8 ton axle load. So total comes out to be 100 ton. And again, the maximum tire pressure which is given in IRC 6 is 5.273 kg per cm square. And accordingly, the size of the contact on the bridge deck is calculated. Again, this is class 70, not 70, this is class A track vehicle. What is different with 70R track and class A? Both are 70 ton 70 ton total load with the contact length is only difference. This is 3.6. It was earlier it was 4.57 and width is 2.9 only, same width. So this is 35 ton, this is 35 ton. Again, edge distance is, this is 1.2. It is given the edge distance of 1.2. This is applicable for 2-lane carriageway width of 7.5 meter. Again, this is class A wheeled vehicle, which is having a maximum vehicle load of 20 ton for a single axle and 40 ton for bogie axle, with a center not more than 1.2 meter. It is clearly given in this sketch below. Again, the edge distance is 1.2 meter only. This is usually adopted when you are designing the deck slab over the girder. So bogie axle we are taking when you are designing the deck slab over the girders. And next load is class A loading, which is total load of class A loading is 55.4 ton. So you are having a 2.7 ton 2 axle, 11.4 is a 2 axle, and 6.8 is a ton axle is 4 numbers. And the length from toe, rear to front wheel is 18.8 meter. And distance between the successive rear successive train from front to rear wheel of the is 20 meter. This is clearly given in the code. And the wheel width, distance between two wheel in the transfer direction is 1.8 meter. So these are the ground contact damage area. Ground contact area is given, tabular form is given. For 11.4 meter, the P is 250 mm and width of the tire is 500 mm. For 6.8, it is 200 and 380 mm. And this axle of 2.7, it is 150 mm and this is 200 mm. Why this is required? Because when you are analyzing any bridge, for live load analysis you are doing, so you have to take the dispersion. So ground contact area is very important. The width of the vehicle is very important because the dispersion along traffic direction and along across traffic direction, the formulas are given in IRC 112 in annexure B. So when you are dispersing you will get a UDL or load intensity on the bridge deck. So that you have to calculate for further analysis to find out the bending moment and shear forces. So these are the minimum clearance for class A vehicle. The clear carriageway width is 5.3 to 6 meter. The G, the distance between the two wheels. This G, when your two vehicles are passing through the bridge in along the lane in transfer direction, G value varies from 0.4 meter to 1.2 meter. So 0.4 meter for 5.3 and for 6.1 it is 1.2 meter. And F is the edge distance from the curve. It is 150 mm. In class 70R wheel or A, it is 1.2 meter. But for class A, the F distance, C distance is given as 150 mm. And above 6.1, the distance of G is 1.2 meter. But edge distance is 150 only. So that how this 5.3, these calculations are again given in the codal codes also. It is 5.3 is 1.8 meter is the center of the wheels and 0.8 is the width of the tire into 2 plus 0.4 plus 2 into 2, 0.15. This is 0.4 is the G distance. So minimum 5.3 is with the 0.4 G distance. And if it is 1.2, it becomes 6.1. That is clearly mentioned. So when you are analyzing and keeping the position of the wheel in the transfer direction of the deck, you have to ensure the which position is giving you the maximum bending moment and maximum load intensity on the deck. Accordingly, you have to design the and do the analysis part. So this is the another load which is usually taken for the temporary structure. This is class B loading. It is similar to class A loading, but it is adopted for temporary structure. For this, usually for the nowadays the class B loading is not taken for the design. This is only for the temporary, where there you have to restrict the load, moving load. So you have to analyze for the class B whether it is safe. Sometimes the bridges get distressed, so you have to reduce the loading. So you have to reduce, find out whether class B loading can be passed on that bridge. At that time, this load calculations are done. So that is similar to class A loading only. Other dimension and everything is same. So this is again 6.8 meter. This is 4. Instead of 11.4, it is given 6.82 load. And instead of 2.7 ton, 1.6 two axles are there. 2 axles of 6.8 and 4 axles of 4.1 ton. And these are again the ground contact dimensions of the class B loading. These are again same what we have seen for class A train. Similarly, G distance is 0.4 to 1.2 and 1.2 for above 8.6, 5.86 meter, and A distance is 150 mm only. Then next, this is the how you are combining the how many lanes you are designing. So purpose of it's a single lane, double lane, 2 lane, 3 lane, 4 lane, 5 lane, 6 lane bridge is there. So how you are taking which type of vehicle you will pass, whether it is class A 70R, that load combination has been given in IRC 6 in a tabular form. When the bridge is having a carriageway of 5.3, only one lane of class A is considered to occupy 2.3 meter, and remaining balance portion shall be loaded with 500 kg per cm square, meter square. This load has to be for analysis I've done for single lane bridge is only for class A with the additional load beyond 2.3 meter, 500 kg uniform load has to be applied. From 5.3 to 9.6, the number of lanes for the design purpose is 2, and one in that case 70R, one lane of 70R wheel or track has to be taken, or 2 lane of class A. We have to analyze accordingly. So this is 100 ton and this is 55.4 into 2. So 110.8 ton load we have to design. Analyze the superstructure. And from above 9.6 to 13.1, the number of lanes are 3. In that case, you have to take 1 lane of 70R for every 2 lane, and with 1 lane of class A for every additional lane, or 3 lane of class A you have to take. And in for above 13.1 meter, and it is less than 16.6, it is a 4-lane bridge. So in that case, for 4, 5, 6, the load combination given is 70R wheel for every 2 lane. So when it is 4 lane, then you have to take 2 70R vehicles for every 2 lane, with 1 lane of 70 class A for the remaining lanes. Means if it is 3 lane, then 1 lane of class 70R and 1 lane, 2 lane of class A is taken. So it is clearly given in the codal how the load combination of live load for class A and 70R, or it should be taken. So this again sketches are also given in the code. If it is one lane, so this is class A we have taken. For two lane, it is class A, two lane or 70R wheel. This is class A two lane and this is 70R one vehicle. In three lane, again three class A vehicle or class A is one vehicle and 70R wheel one vehicle. So these sketches are self-explanatory, which are given in the code, which has to be followed when you are analyzing the bridge or different lane as per the general element drawing. What is the requirement? Whether it is two-lane bridge, three-lane bridge, you have to analyze accordingly for the live load. So I will not cover all these things. The sketches are given in the code, IRCC code. Now, this is one load, which is special vehicle load. Nowadays, we are designing all the bridges for SV loading, which is usually applicable in the industrial area. So this special vehicle, when you are designing, the total load of the vehicle is 385 ton, which is having a 20 axles of 18 ton. So this is 360 ton. And prime mover is a 6 ton for 6 ton plus 9.5 into 2 axles. So this total comes out to be 385 ton. The length of the vehicle, total vehicle is 38.459 meters. So this is the heaviest vehicle. This is usually very critical when the bridge length is more than 15 to above 15 meters. So this becomes a critical in the analysis. But there are some special provisions given in the codal when you are using the special vehicle, what other load combination we should not take. That is further elaborated. You can see this width of the SV load vehicle, special vehicle is 3 meters, and ground contact dimensions are also given. This is B is 156 mm, and width of the each vehicle is 274. So there are how many? 1, 2, 3, 4, 5, 6, 7, 8 wheels are there. 8 tires are there with the maximum load on each tire is 2.25 ton. That is 2250 kg. So if you find out this pressure with this, it is less than 5.273 kg per cm square, which is giving the maximum tire pressure in the IRC6. So when you are analyzing for the special vehicle, the special
Recording
vehicle has to be
stopped. Recording in progress.
The special vehicle loading should be seen when you are analyzing it. It should pass to the CG of the carriageway.
Recording stopped.
Or with maximum eccentricity
Recording
of
in progress.
300 mm. Okay. 300, what maximum eccentricity for the special vehicle given is 300 mm for single carriageway bridges or for dual carriageway bridge. So what are the provisions for the consideration of the SV loading is, when you are considering SV loading, during the passing of SV loading, no other live load including footway load or shall be considered to ply on the same carriageway. Means when special vehicle is moving on the bridge, no other live load is to be considered. Whether it is 70R or footpath load, nothing has to be considered in the analysis. And effect, when you are combining the load combination, effect of wind, seismic, temperature should not be considered for the load combination with SV loading. And third is the tractive force or braking force or dynamic impact on the live load need not to be considered on the carriageway carrying the SV loading. When you are analyzing for SV loading, shown longitudinal forces, which are tractive forces, braking force, or impact force, should not be considered. For load combination with special vehicle, partial safety factors for verification of equilibrium and structural strength and strength of the foundation under ultimate threat shall be limited to 1.15. So only when you are analyzing with the SV loading, the partial safety factors is 1.15 only. And for verification of serviceability limit state, the including live load surcharge, for partial factory factors are only 1 under rare combination and 0.75 under frequent load combination. The movement of SV loading shall be regulated to monitor to ensure that it moves at a speed less than 5 km per hour. This is very important. When SV loading is moving, the movement speed of the vehicle is 5 km per hour only, and does not fly on the breeze with high wind condition. When there is a wind condition is more than 36 or 47 km per hour, the vehicle, special vehicle should not fly on the bridge. That is the condition. So these are the just a sample calculations from the SV this STAD. If this is 25 meter span, how the analysis is done in STAD for moving load? We have to run the load and find out the position of the maximum position of the load for maximum movement and shear force from the STAD. These are the sample snapshots from the STAD models. This is for 70R class A. This 70R wheel loading. This is track and this is special vehicle. So one more vehicle which has to be checked for the fatigue of the bridge is a fatigue load. This load is total load of this is 40 ton. So the spacing of the vehicle wheel is 1.4 meter rear and front it is 4.5 meter. This is 14 ton axle, this is 14 ton axle. Again here also maximum tire pressure is 5.273 and with the ground contact is given as 710 for two tire on both the sides with a 310 each tire is given in the code. So when you are analyzing, this is giving the congestion factor now. The slide shows the congestion factor for flyover, grade separator close to the areas such as port, heavy industries and mines and any other area where frequent congestion of heavy traffic may be decided by a concerned authority. An additional check for congestion of vehicle, of live load, vehicular live load on the carriageway shall be carried on. When there is a heavy congestion in the city area or near the port, on the bridge, all the vehicles are on the bridge itself stand still. So that factor has to be taken based on the span arrangement. In the absence of any stipulated value, the congestion factor as mentioned in the below table. The table is given in the IRC 6, table 8. Considered by multiple factor on global effect of the vehicle. So when you are doing the vehicular live load analysis, so you have to apply the congestion factor in it and see that the bridge is safe for that congestion load. So now, so when there is we have completed the analysis of the vehicular live load analysis of the bridge. There are one more factor is there, that is impact factor, that is known as dynamic factor or dynamic action that may be made by increment of the live load by impact allowance expressed as a fraction of percentage to be applied in the live load. So you have to enhance the vehicular live load by a factor based on the span arrangement for different types of vehicular live load, that is class A 70R. The formulas are given in the code. Here, this is a, if class A or class B loading is there, the impact factor fraction for reinforced concrete bridge is 4.5 divided by 6 plus L. And impact factor for steel bridge, it is 9 divided by 13.5 plus L. L is nothing but a span length. So this is some calculation up to 45 meter I had done randomly. The table is giving when the span is 3 meter. So this is applicable from 3 to 45 meter. When the span is 3 meter, the impact factor is highest. It is 0.5 for reinforced concrete, and steel bridge it is 0.55. As the span goes on increasing, impact factor goes on decreasing because span is in the span length is in the denominator. So as the span increases, the impact factor goes on decreasing. These are calculation for this. This is for the class A and class B loading. So when the class AA or 70R loading is there, they are specified for the span less than 9 meter. The impact factor is 25% up to 5 meter and linearly reducing to 10% for span up to 9 meter. Means for trike vehicle, if the length of the bridge is 9 meter, the maximum impact factor is 10%. And when it is 5 meter, maximum impact factor is 25% for trike vehicle. And for wheeled vehicle, the impact factor is 25% up to 9 meters. When it is more than that, 10% for span up to 10 meter, it is given for the trike vehicle. And in accordance with the curve for the spans in exceeding 40 meter. So when the table curve graph is given in the IRC code, that it is followed when the span is exceeding 40 meter, then you have to follow the graph and find out the impact factor. And for wheeled vehicle, 25% for span up to 12 meter, and in accordance with the curve for span which is exceeding the 12 meter. This is for RC bridge. And for steel bridge, again, it is 10% for all span for track load. And for wheeled vehicle, it is 25% up to 23 meter. And in accordance with the curve, again, above the exceeding 23 meter. So this is the graph. If it is above, then you have to follow this graph and find out this is the span and this is impact factor. So we have to take as per the graph for the steel bridge and for RC bridge. This is the percentage for 3 meter or less, and this is 55.5 is the maximum percentage for 3 meter or less. This is for steel bridge, this is for RC bridge. The graph is given. So this was the main topic for vehicular live load, because main vehicular live load is very important in the analysis of any bridge. Vehicular live load is very important. So next important load is horizontal forces. So this, because of live load, that is a vertical load which is acting on substructure. It can be a vertical load with the eccentricity from the CG of the pier, which gives the movement due to the differential reaction, or considering the one span of condition, or vehicle on one side only and other span is not loaded, and one side it is loaded, it will give the maximum movement. So when you are designing a substructure, you have to find out the maximum reaction case and maximum movement case. These reactions are very important when you are designing the substructure. So you have to run the vehicular load and find out based on the span what is the reaction on one side, when the bridge is loaded on one side, what is the maximum reaction? And when the bridge is loaded on both the sides, what is the maximum reaction coming on the pedestal and subsequently transferred to the pier and foundation. So that maximum movement case and maximum reaction case is very important when you are analyzing the lie load when designing the substructure. So next load is what horizontal load due to water current. So when you are designing a river bridge, the during the floods, there are a lot of news are there. This bridges are getting washed away and they are getting settled. You have seen during the floods, this news every year it comes. This bridge has been washed away, this has been flooded, or whether it is submersible, then the bridge is submerged and no vehicle is flying. If the bridge is designed for the submerged load, it will sustain after the flood. If it is not designed as a submerged bridge, then the superstructure of the bridge or the pier is getting washed away. So there is a total fully damage to the bridge, and again you have to reconstruct it considering the subsequent factors of analysis as a submerged bridge. So water current, when you are designing the bridge for water current, the water current, you should first initially do the hydraulic of the bridge. What is the maximum velocity in that area based on the discharge, and what is the influence of the catchment area, maximum rainfall intensity. These all things were yesterday covered by Mr. Desai and Mr. Khare, how to find out the maximum discharge and velocity in yesterday's session. So this is after you are getting the velocity and discharge, what factor we require is the velocity basically and afflux. So if you know the velocity, the pressure acting on the bridge component, water pressure acting on bridge component is 52 kV square. This is the formula. This V square is the velocity. This velocity is root 2 times the mean velocity of the water current. And K is giving the factor based on the shape of the pier. When it is square pier, the factor will be different. When it is a round pier, the factor is different. If you see, this is a photograph of one of the bridge we have designed. This is a flood of Tapi River bridge construction. And when it was under construction, you can see this total area flooded with the velocity. In this Tapi River, the velocity was around 6 meters per second. And you can clearly see how the eddies are formed and how the afflux is taking place. So when there is a bridge pier, there is a this eddies effect is there, and on the side of the pier there is a static action, static water pressure is acting in the transfer direction. So this you can see this is the K factors table is given in the IRCC. When the pier is square-ended pier, and for the superstructure, the K value is to be taken as 1.5. If the pier is circular with semi-circular edge, the K is taken as 0.66. So if you see, when you are deciding the pier shape, usually in the river bed, when there is flowing water, the pier should be semicircular. So because your water current forces will reduce more than 50%. Again, when the pier is taken in the cut and ease water, triangular shape, further there is a reduction in the K factor, it goes to 0.5. The pier with regular cut and ease water and angle included between the faces being more than 30% but less than 60%, then K value should be taken accordingly from 0.5 to 0.7. A pier with triangular cut and ease water, the angle included between the faces been more than 30%, but less than 60 to 90%. Again, it factor goes in to 0.7 to 0.9. Similarly, pier with cut water of equivalent arches of circle, then it is 0.45. And pier with arc of cut and ease water intersecting at 90 degrees is again 0.5. So usually these are the factors which has to be considered when you are finding out when you have to find out the pressure on pier or substructure. So when you see in any force calculation due to water current, the velocity of the water is maximum at the top and zero at the score level. Point of deepest score of score level, it is zero. It is a triangular. So the free surface of water is giving the maximum velocity. And intermediate you have to calculate based upon the depth you require based on the formula V square is equal to under square root of V mean velocity into x by h. So that velocity you will get at the x from the deepest point level. And then you have to work out the pressure diagram. And then from pressure diagram, you have to work out the forces acting by multiplying the cross-sectional area of the pier or obstruction which you are which you have to consider. It can be, if it is submerged bridge, then you have to take the obstruction of superstructure also and find out the force acting on superstructure, and that will create a movement in pier. And accordingly, suitably, you have to design the stopper if it is a submerged bridge. So one more point is given in IRC 6. What we have initial talk was for the water current which are normal to the direction of the pier. So sometimes what happens, there is a meandering of the river or there is a scoring action taking place. The water current forces get diverted by a maximum angle. What they are given is 20 degree. So when you are designing a bridge for normal current, then you have to consider a skew current also and resolve the forces in longitudinal and transverse direction for the design of foundation in pier. That variation allowance has been given in the codal provision IRC 6, which variation is in the tune of maximum 20 degrees. But when there is a pier, which when the flow itself is in the skew direction, then you have to take 20 degree plus skew direction, and accordingly you have to resolve the forces. That provision has been given in IRC 6. So, and further they are given in case of the bridge having a pakka floor where there can't be a scoring or non-erodible bed, the effect of water current, cross current, shall in no case be taken as less than that of the static force due to difference of head of 250 millimeter between the opposite faces of the pier. So when you are calculating the water current in the upstream side, the downstream side, you have to calculate the static force gamma into h, which is 250 mm less than water current height on the upstream side. And one more provision they are given when you are going for the multiple column or trussel column. If they are closely spaced, it is placed less than 3 times the center of the column. Then you have to take it acts as a solid rectangle with a K value of 1.25. Though if there is a column or circular column, but if it is placed at 3 meter center to center or lesser than that, then you have to take it as a solid with a K value of 1.25. If it is greater than 3 times, then you can take a K factor 0.66 for a circular column accordingly and analyze the design for water current forces. And if it is less than 3, if the pile and column are braced, if they are freely standing, then you have to take 1.85. If it again there is bracing is done to the column, then you should take a water current force with a K value equal to 1.5 with a full area, solid area of the columns. Because what happens when it is braced, then lot of debris coming during the flood gets stuck it and the water current forces enhances very much. So if it is braced, then you have to take the full solid section with a K value of 1.5. The next force which is to be considered is the buoyancy. So if you see the buoyancy, to allow for the buoyancy, there is a reduction of the gross weight of the member affected by reducing the density of water displaced. So volume of water, this is nothing but the Archimedes principle which you are following. So weight of volume of a body submerged in a water, that much volume into density of water, if you multiply by density of water, means it is equivalent to the volume of solid. That much reduction weight you have to take as a buoyancy weight. And when you are designing a submersible pier, masonry or concrete substructure, the buoyant effect through pore water pressure can be limited to 0.50% of the total buoyancy. So in case of submersible bridge, the full buoyancy effect has to be considered for the design of superstructure. Not design of superstructure, full buoyancy effect on the superstructure shall be taken into consideration. So you have to reduce total weight of the superstructure by total volume of superstructure. So weight on the substructure will reduce, and with reduced weight, you require more foundation area and more cross-sectional area of the pier. So you have to be very careful while you are designing the submersible bridges. So next important force. Now what we consider is a water current force. When there is no water, which are the longitudinal forces acting on the bridges and why they are acting and how they are acting? That is very important, because finding out the vertical load on any substructure is okay, but main design of any substructure is governed by the longitudinal forces. So what are the longitudinal forces on the bridge is arriving from which actions? One is the tractive efforts due to acceleration of a vehicle. When we are accelerating the vehicle on the bridge, the contact between the tire and the bearing force gives the frictional force, that is the tractive force when you are accelerating. When you are applying the brake also produce a horizontal force on the bridge in the direction of the traffic. So braking resulting from application of brake on the brakes on the bridge deck. And one more force is frictional resistance. Friction resistance offered to the movement of free bearing due to change in temperature and other cause. Temperature, other cause means shrinkage, creep are also the factors which create the frictional force through the bearing. And that horizontal force developed, frictional force developed, is transferred to the pier and foundation. That is very important. So frictional force, this or longitudinal force, in this case, it is in braking force is greater than tractive efforts. So usually braking force is considered in the design of bridge for the longitudinal forces in the direction of the traffic, in longitudinal direction. So especially when you're talking about the braking force on simply supported span or a continuous unit of span or any other part of type of bridge unit having the following value. So how much braking force you have to take? That has been clearly given in IRC 6 clause number 11.2. In this case, when in the case of single lane bridge or two lane bridge, that is equivalent to 20% of the first train plus 10% of the load of the succeeding train. The 20% is there, and beyond that, one train is, if class A train is there, it is 55.4. So 20% of it is 10.8 ton, 11.8 ton. When succeeding train is further 55.4 ton class A train is there, so you have to take only 10% of it. So it is 5.4. So accordingly, you have to less, because when the bridge span is less, if it is up to 20 meter, then only 20% is applicable. But if the bridge length is beyond, it can be 20 plus 18.8. So beyond 40 meter, the second succeeding train will come in picture. So in that case, you have to take the braking force of 20% plus 10% of the succeeding vehicle. This is very important for long bridges. When this is for two lane, again when the lanes are more, then what you will do? Then that is clearly mentioned. It is same as clause A for two lane, but you have to only add 5% of the lane, extra lane, vehicular lane, 5% of the load of additional vehicle on side vehicle for excess of two lane. It is clearly mentioned. So when braking force is applied in the direction of traffic, at what position or what RL it is acting? It is acting at 1.2 meter from the RTL of the bridge. So you have to, accordingly, you have to take the movement part and find out the push-pull reaction on the pier and add or subtract the force or a vertical load. So this is one more slide. This is for frictional force on pot PTF bearing. So we have covered the braking now. If the bridge is simply supported and supported by the pot PTF bearing, when you have for simply supported, one side bearing is fixed bearing and another side bearing is free bearing. So how much force you have to consider? That is very important. So when if you see for fixed bearing, if it is FH minus mu RG plus RQ. And for free bearing, it is mu RG plus RQ. So what is FH? FH is the applied horizontal force. So which is applied force? What we have discussed now, that is braking force is the applied horizontal force. When you are applying the brake to the vehicle, the horizontal force which is acting at 1.2 meter above the RTL, is the applied horizontal force. And RG plus RQ is nothing but it is a reaction, dead load reaction. RG is a dead load reaction of the free bearing or fixed bearing, and RQ is again the dead load reaction. Live load is a reaction. RQ is a live load reaction on free bearing, and mu is the coefficient of friction of the bearing. In this case, clearly shows this is applied horizontal force. Applied horizontal force can also be a seismic force. So this is mu RG and mu RG. It is acting this. This is your fixed bearing and this is roller. So this is acting in opposite direction. This is acting in this direction. This when this H is the horizontal force, this is taken as H by 2 plus RG plus RQ. This is the horizontal force. In case of the fixed bearing, FH by 2. And this is FH by 2 minus mu RG. So this is clearly mentioned. FH is the horizontal force, mu RG plus RQ is the frictional resistance of the free bearing. So what you actually are doing, this is horizontal force. This is free bearing is the frictional force acting in opposite direction. So you are directly subtracting from the fixed bearing. And this is one condition. When you are taking half of the FH, then you have to add mu RG plus RQ because it is acting in one direction. And this is mu RG plus RQ is the for free bearing. So what is mu coefficient? How you will consider it? So that code has given the different types of roller bearings or different types of bearing, and frictional coefficient has been given. So there, for roller bearing, the mu is 0.03. For concrete roller bearing, it is 0.05. Again, for sliding bearing, steel on cast iron, it is 0.4. Again, these coefficients are mu coefficients are given in the codal provision. Accordingly, you have to take. And now, when there is elastomeric bearing, in simply the when you are using the elastomeric, so how you will find out the horizontal force when you are using the elastomeric bearing? It is based on again FH by 2 plus mu RG into ITC. So ITC is the movement of deck above the bearing other than that of due to applied forces, that is strain due to creep, shrinkage and temperature. So when there is expansion or contraction of the superstructure, that force is that movement is calculated, and accordingly the force is calculated on the elastomeric. So FH by 2 is nothing but breaking force divided by 2 on each bearing, and this is VR is the shear rating of the elastomeric. VR is based on the area of the bearing and shear modulus and divided by thickness. If you are increasing the thickness, your shear rating will go on reducing. So your horizontal force is reduced. When the thickness of bearing is less, horizontal force due to friction is increasing. And one more thing, when you are using the neoprene bearing, this is a pier, and this is a one pedestal. Sorry, this is another pedestal, and one bearing is here and another bearing is here. So the action is in opposite direction. This force is acting in this direction, and another force is acting in this direction. So this neoprene bearing, if you are using the force is nullified, so balancing each other. But you have to design for some horizontal force. Now, what horizontal force is there is to be taken is 10% of variation in the movement. It is given in the subsequent clause below. So 10% you have to take. You have to find out the force, and 10% of this you have to take for the design of the substructure for horizontal force. due to horizontal force, longitudinal force due to friction, bearing friction. And now next gives the horizontal force due to continuous span. When continuous span is there, again there are fixed bearing, free bearings. So we have to consider the bearing on the left side or right side, how many bearings are there. Accordingly, you have to calculate the force on fixed bearing. What happens when there is a three-span continuous? The one bearing is only, one pier is supporting the fixed bearing, others are totally free. So free bearing is having horizontal force based on the friction and reaction. But what about fixed bearing? Fixed bearing is having free bearing on right side and free bearing on left side. So difference of it is a positive. Then you have to take as a positive. FH is the braking acting in the positive direction. And if FH is greater than 2 mu r, then you have to use this formula. If it is less than 2 mu r, then you have to use another formula. So this exercise you have to do before you are designing the fixed pier supporting the fixed bearing. So these two cases are there, case 1 and case 2. This is mu r minus mu l. This is mu r minus, this is positive, but FH is acting in negative direction. So accordingly, you have to work out all the probabilities and find out what is the maximum force due to longitudinal force due to bearing friction is coming, and design the pier for the maximum of the longitudinal forces. Then apart from longitudinal force, now next force is centrifugal force. This centrifugal force is generally acting on the bridge which are curved, having bridges which are curved in plan. So what centrifugal force, everybody knows what is centrifugal. Centrifugal force is force exerted by the vehicle with a speed and having a certain radius of curvature. And it depends upon the total weight of the vehicle also. So formula that C is nothing but a centrifugal force. This force is acting in transverse direction. That is acting perpendicular to the movement of the traffic. So centrifugal force is W V square. V is the design speed of the vehicle, and W is the weight of the vehicle, and this R is the radius of the curvature. So this you have to find out and apply in that direction when the bridge is curved. And this force is again acting at a depth height above RTL by 1.2 meter. This force I consider to act as 1.2 meter above the level of carriageway, RTL. So no, in further the clause says no increase of impact effect shall be made on the stresses due to centrifugal force. So this relaxation is given where you increase in impact. We can avoid taking the impact factor while finding out the stresses in the member. Then, and the overturning effect of centrifugal force on the substructure as a whole shall be duly considered. Overturning effect you have to consider fully. When the centrifugal force is acting, then you have to find out what is the overturning movement acting on the pier and see that it is stable. The next force is earth pressure. When you are designing abutment, which is a part of the bridge component, or retaining wall, that is return wall, your earth pressure is a very predominant force for which you have to design it. So when there are two types of earth pressure, one is active. Active is acting and other passive resistance. Passive is a force which is stabilizing force. Active is usually active pressure is taken in the design, passive we are neglecting it because sometimes in river bridges and score action is taking place. So we are not taking active in resisting force to the stabilizing force. So this earth pressure is based on the Coulomb's earth pressure theory, which is giving the formula to find out the coefficient of earth pressure, active earth pressure, which is based on the angle of internal friction of soil and the angle of earth face to the wall, which makes it the vertical. This is the angle. And slope of the earth field. This is slope. Beta is the slope of the earth field. It is inclined surcharge. And the active earth pressure will change. And one more is the friction between the earth and wall. So that is usually taken delta, which is 2/3 of the phi we are taking. It's subject to maximum of 22.5 meter, 5 degree. When you find out the active or coefficient of earth pressure, then the application for the design of wall is 0.42 meter above the base. And when you are considering the weight condition, then you have to consider 0.33 H. So these are again the passive earth pressure formula. And same formula, but with some changes in the empirical notations, plus minus. And accordingly, you have to work out the passive pressure wherever you require. For design or retaining wall, you can require the passive earth pressure. Sometimes in abutment for flyover, you can take advantage of passive earth pressure by taking it as a stabilizing force. And point of application of the passive pressure is taken as 0.33 H, which is above the base for both wet and dry condition. Then one more coefficient is there, that is coefficient at rest. So when you are finding out the coefficient at rest, it is based on the Rankine's theory, then 1 minus phi, sin phi. So usually that is factor is 0.5. At rest, K naught is usually taken as 0.5. That is earth pressure at rest. And this is usually applicable when there is no movement in the or deflection in the vertical stem. When there is no deflection, then the pressure is increasing. When it is deflecting, the pressure is equal to Ka. That is active earth pressure. Means it is deflecting, so the mobilization of the earth pressure is reduced. When it is at rest, the earth pressure is increased. So usually it is 0.5, and this is usually used in the design of the box culvert, because box culvert is an integral box which doesn't deflect because it is rigid enough, so there won't be much deflection. So usually the box culverts or box cell structures are usually designed by coefficient at rest. And the application of the earth field at rest is usually taken at 0.33 of H. And this is the force. When you are designing any retaining wall or any earth retaining structure, what are the forces acting is clearly mentioned in this sketch below. If you see, there is one more force is there. This is vertical force. This is what P vertical, which is usually acting at the virtual back of the retaining wall. When there is this raft is there, this is a toe and this is heel. If the end of the wheel, that V is acting. If this is usually taken and it helps in the stabilizing the movement of the, when you are calculating the stability of the retaining wall, this PV plays an important role in stabilizing the force. And other is this is sulfate of the weight of the soil acting on the heel, and this is sulfate of the stem, and this is sulfate of the raft. So this is this example you can see in any books also. You can get and design the retaining wall or retaining structures. One more load which is acting on the design in the design of the earth retaining structure or abutment. It is live load surcharge. What is live load surcharge? When the beyond the abutment, when the vehicles or movement is there, they are flying from the earth to the bridge. So that surcharge due to live load, which is equivalent to 1.2 meter height of the equivalent earth load, is to be considered when you are designing the abutment for live load surcharge. And one more important is that live load surcharge need not be considered for any earth retaining structure beyond 3 meters from edge of the formation. When there is a retaining wall is there and your carriageway is 3 meters away from the hay, then you need not have to consider the live load surcharge. But when it is just at the edge of the carriageway, retaining wall is there, then you have to design for live load surcharge. Now next load is wind load. Wind load is very important where the wind intensity is very high in coastal areas and all this thing. But usually all the bridges are designed for the wind load checked. Usually wind and seismic load combinations are not combined together. When you are taking wind load combination, the seismic will be not there. When you are seismic you are taking, then wind load loads are not in combination of that load combination is considered. Excuse me.
Yeah, I think, and Manjwani, I think you should have some water. You have been,
Yeah, thank you. Because
and
already it is.
yes, so you have got around another 10-15 minutes. I think.
I'll complete now. Only one load is balanced.
Yeah.
Wind and seismic is balanced. But I'll
It is
complete.
going nice.
Thank you, ma'am. And so, in the wind load clauses, as per IRC 6, this clause is applicable to normal span bridges with individual span length of 150 meter or for bridges with height of pier up to 100 meters. So this is clearly mentioned. The wind pressure acting on a bridge depends on the geographical location, terrain surrounding area, fetch of the terrain wind, upwind of the site, and local topography, the height of the bridge above the ground, horizontal dimensions, and cross-section of bridge or its element under the consideration. So there are a lot of factors for which wind pressure is calculated. So when you say the hourly wind speed and PZ values corresponding to basic wind pressure of 33 meters per second, return period of 100 years is considered. The longitudinal force on bridge superstructure shall be taken 25% and 50% of the transfer wind as calculated on for beam, box, plate girder and truss bridges. This clause, see, there wind force is acting. If wind force is acting in transfer direction, then what about the skew wind? So you have to when you have to calculate the wind for pressure on in transfer direction, and 25% you have to take as in longitudinal direction, and 50% you have to take in transfer direction. In that case, you have to resolve the forces and you calculate the movement in both the direction for designing of the substructure. The exposed frontal area of the live load shall be entire length of superstructure seen in the elevation in the direction of the wind as defined in clause, or any part that length produce critical response multiplied by the height of 3 meters above the road surface. And one more, the bridge shall not be considered to carry any live load when the speed of wind of the deck is exceeding 36 meters per second. When the wind velocity is 36 meters you are considering, then you should not take a wind on live load. It can be neglected. So these are the hourly mean wind speed and wind pressure for the basic wind of 33 meters per second. This table is given in IRC 6 in table 14. Based on the height, the plane wind velocity and pressure are given directly in plane area and with obstruction. If there are obstruction, their velocity, wind velocity is less or speed is less, pressure is less. When there is no obstruction, it is plane, then the wind speed is more and pressure is also more. This table is directly given in the code. And this is for the basic wind speed of 33 meters per second. If the wind speed is higher, then you have to multiply by the ratio and find out, calculate the wind speed and pressure. So this is the graph which gives wind pressure in regions. If it is clear, with wind pressure of 56. 1 second. If you see, this is the orange color which is giving the wind speed of 55 and 47 is green color. This area is totally having wind speed of 47 and minimum wind speed is 33. It is in this region. This region 33 and yellow is your 36 or 39. 39. This is 39. So this wind graph is already given in wind map is given in the code, and accordingly in which region you are constructing the bridge and wind speed, you can consider that accordingly and find out the wind forces. So when you are designing the force, the transverse wind force shall be acting at the centroid of the appropriate area and horizontally shall be estimated as Pz. This is wind speed into area into gust factor and drag factor. This is gust factors which is usually taken as 2 and drag factor is based on the size of the pier. If it is greater than 10, it should be taken as 1.1 or it is given in the table form based on the size, shape of the pier. So accordingly, you have to work out the drag factors. Again, one more wind force is there, which is acting in vertical direction. So this wind force, again, same wind force into area into G into CL. CL is the lift coefficient, which is usually taken as 0.75. This check is also very important in high wind speed region bridges. The design of wind force on substructure. The substructure should be designed for the wind induced load transmitted to it through the superstructure and wind acting directly on the substructure. So one is the wind acting on the superstructure which is transmitted through bearing or through pier cap to the substructure and directly wind acting on substructure. Both you have to take combined and design the substructure accordingly. So this is the table to calculate the drag coefficient based on the shape of the element. Based on the L by B, the ratios are given and the depth to breadth ratio is also given, and accordingly you have to calculate the drag coefficient or interpolate if the depth to breadth ratio is in between 1 or 2, then you have to interpolate the values accordingly and calculate the wind force. So next is the seismic force. Actually, seismic force is a major force in seismic area, and this seismic force is basically a very important force acting in seismic regions, basically zone 4 and above. Zone 3 also it is very important. We are designing the bridges and taking into consideration the seismic force for 3 also, and check for the stability and other things. This topic of seismic analysis and design will be further covered by Mr. Professor C.V.R. Murthy. So I will not go in detail in this, only basic things I will explain as given the codal provisions. What code says, the following bridges should not be checked for the seismic effect which are that bridges when it is a culvert. For culvert, we need not have to design for the seismic, or minor bridge, the bridge up to 60 meter, but the span is less than 10 meter. Then you need not have to design for the seismic. In all zones, whether it is in zone 4 also, the culvert and minor bridges up to 10 meter spans are not designed for seismic. And second clearance is that the bridges seismic zone 2 and 3 satisfying both limits of total length not exceeding 60 meter and span not exceeding 50 meter. In zone 2 and 3, you need not have to design this bridge for seismic loads if it is a span is not exceeding 15 meter or length of bridge is not exceeding 60 meter, 15 and 60 meter. So when you are calculating the seismic force, what force is to be calculated is the horizontal force. So how will you calculate the horizontal force? Horizontal force is calculated by one horizontal seismic coefficient, that is AH. AH into weight of the structural component, appropriate weight of the structural component, and live load, appropriate live load. So that is AH is based on what? It is based on the zone factor. It is based I means importance factor, R is response reduction factor, and SH by G is the response acceleration coefficient, this is based on the fundamental time period for horizontal vibration. So this is the basic formula. This is seismic force. Earthquake seismic force is equal to AH into dead load and appropriate live load of the on the bridge. And this further, to calculate the natural time period T in second for pier or abutment of the bridge along with the horizontal direction may be estimated by following expression. So what T is 2 under square root D plus 1000 F. What is D is the appropriate dead load of the superstructure and live load in kilonewton, and horizontal force in kilonewton required to be applied at the center of the mass of the superstructure for 1 millimeter deflection. 1 millimeter deflection at the top of the pier abutment or for the earthquake in transfer direction, and force to be applied at the top of the bearing for the earthquake in the longitudinal direction. So this is the fundamental natural formula for calculate the time in second. Accordingly, what is time in second coming, then you have to calculate the SA by G. This is the graph which is given in the code, which is giving the seismic zones. Zone 2, 3, 4, 4 and 5. So this is the table according to zone factor. Zone 5 it is 0.36. Zone 4 it is 0.24. Zone 3 it is 0.16 and zone 2 it is 0.1. The importance factor is again based on the type of bridge. If it is normal bridge, then you have to take the importance factor as 1. So if it is important bridge, river bridge and for inside the city, bridge on NS and state highway, bridge and serving traffic near port and other center of economic activities, and bridge crossing the railway line. So you have to design for 1.2 meter important factor. The large and critical bridge in the all seismic zone, long bridges more than 1 kilometer across the perennial river and creek, and bridge for which alternative routes are not available. Then you have to design for important factor of 1.5. And this again response reduction factor is given based on the what type of ductile detailing you are going to do. If you are doing the detailing of reinforcement with ductile detailing, then the response reduction factor are different. When we are doing without ductile detailing, response reduction factors are different. So this enhances your seismic coefficient if you are not using the ductile detailing. This given the table in IRC 6. So next force is temperature. So where it is used? Usually temperature force is usually taken for the rigid bridges or integral bridges where there is a restraint to the movement. When you are not using the bearings and you are connecting the substructure and superstructure with a rigid connection, the temperature effect plays very important role, because this does not allow the expansion of the superstructures. So there is a horizontal expansion which is not allowing. It will create a force in the horizontal direction and will create the bending moment in the substructure as well as in superstructure. So temperature effect is due to daily and seasonal fluctuation in shade air temperature, solar radiation, and cause the following. One is a change in the overall temperature of the bridge, referred to as the effective bridge temperature. Over a prescribed period, there will be a minimum maximum together with a range of effective bridge temperature, resulting in loads and load effect within the bridge due to it. This is restraint offered to the associated expansion and contraction in the form of the construction. For example, portal frame, this is the arch, flexible pier, elastomeric, referred to as a temperature restraint. When you are using the elastomeric bearing, the force of the temperature will be taken by the elastomeric bearing. When you are designing the elastomeric bearing, you have to consider that. So you have to allow that movement in the bearing itself, so that your force further is not transferred to the substructure. When you are using the friction or roller bearing, so there is only frictional force will act. Direct temperature force will not be coming into picture. Secondly, the difference in temperature between the top and this is top surface and other level. This is due to the temperature gradient basically. This top surface of the superstructure or which is exposed to the sun is directly exposed, that becomes heat and bottom is not heated. So there is a temperature gradient effect is there, which further produces the internal stresses in the member. The provision shall be made for stresses or movement resulting from the variation in the temperature. So that provision has to be made when you are designing the structural member and finalizing the reinforcement. So further, one table is given in the range of bridge temperature and how you have to consider the temperature variation when you are designing the temperature forces. If the bridge is having a temperature difference between maximum minimum air shear temperature, This air shear temperature in IRC6 one table is given to particular location, what is the maximum temperature and what is minimum temperature. And that difference, if it is greater than 20, then you have to calculate the maximum, minimum air shear temperature, mean of maximum and minimum air temperature, plus minus 10 degree, whichever is critical. So accordingly, you have to design, you have to calculate the mean of maximum, minimum, 2 naught means maximum T1 plus T2 divided by 2. Then again, you have to add and subtract the value and find out which is critical. And if it is less, plus minus 5%. According, and for snow-bound area, the extreme range is from minus 35 degree to plus 50 degree. And other areas where maximum air shear temperature is 15 degree to minimum air shear temperature of minus 10 degree. So this is also graph which is giving the maximum temperature in that region. The isothermal lines are given. This is for maximum and this is for minimum. And accordingly, you have to calculate what is the variation of temperature for which you have to design the bridge. The temperature difference, effect of temperature within the superstructure shall be derived from positive temperature difference, which occurs when the condition of such solar radiation and other effect cause gain in the heat through the top surface at the superstructure. And again, there is a reverse in temperature because when you get heated, so again there is reverse action takes place in the night. This is in the daytime, the top surface is getting heated, and again in the night, the reverse temperature takes place. So accordingly, you have to find out and do the design for the temperature. So this is the temperature difference gradient given in the graph, and accordingly you have to find out the internal movements and provide the steel accordingly. This is the temperature effect. Then there is a crash barrier design. The crash barrier design moments and forces has been given in the IRC6, which will not go in detail now because there is a time constraint. Already it is 4 o'clock. This is again barge impact collision.
Manjuwari, I think you'll have to hurry up, I think.
Yeah. The barge impact I will not consider in detail. The collision load has to be taken where there is a navigational span is there. A snow load is usually taken in the snow area where the snow is predominant. In that case, the clauses are given in the IRC6. Second effect is usually for the steel structure is major, and info also second effects are there due to movement of support or deformation when there is integral or restraint bridges are taken. Now again, erection stresses during construction that is considered. So further, one more main topic is load combination. So IRC6 is given load combination based on the partial load factors in the tabular form, and load combination is usually ULS load combination, SLS load combination, which is related to stress and crack width. These combinations will be covered in the next session by Mr. Umesh Rajashekar also, with how the ULS design is done, how the SLS design is done. In that will be covered. So I am not going in detail. So this table are partial factor safety factors for equilibrium is given in table B1. In B2 again it is giving for ULS design, and these are this is again B3 is giving the rare combination for the stress check and frequent combination and quasi-permanent combination for the crack width. This is the B4 table is giving the load factors for the design of the foundation and base pressure. These are the usually normal load combination. How it is done, I put as one small slide. How we are considering no load, live load case, dead load SIDL, and normal load combination, wind load combination, transverse seismic, longitudinal seismic is done, and all the loads are combined together with the partial factors, and maximum bending moment and axial forces done. By this, I'll complete my presentation. Thank you.
Thank you.